Hi y'all, welcome to another round of physics and run a couple more example problems dealing with torque before we keep moving. So, let's go at it. Boom. A grinding wheel is a uniform cylinder with a radius of 0.67 centimeters and mass 8.17. Just some random numbers generated. Determine, number one, its moment of inertia about its center, and number two, the torque applied, the applied torque needed to accelerate it from rest to some RPM in some time. And it's known to slow down from some other, RPM to some other time. Okay. Well, let's go at this. So, number one, moment of inertia about the center. Well, we know how to do that. Let's look up our handy dandy chart. Okay. And we see that, hey, wait a minute. Okay. So I have a disk that's rotating, and let me specify the rotation axis, right? Oops. Okay. So we have our rotation axis. Well, shoot, we better set up a coordinate system if we're going to do that. So let's go ahead, call that y, I'll call this x, and we'll call z out of the board. And we notice, okay, well, maybe I'll draw this a little bit more accurately. Let's go ahead and give this some three-dimensional shape. So it's rotating about an axis through the center. Now it has some sort of three-dimensionality to it. And looking at our chart, we see that this is essentially a cylinder. Or about center. And so we see that, okay, well, the moment of inertia of this object is simply equal to the 1/2 mass of the object, and I'll use big R for the radius of the object squared. Well, at this point, we're just dealing with the plug and chug. So 1/2, I'm given the mass, of course. 1, 2, and rather massive object, but the radius is really small, right? It's 0.0687, and don't forget the squared. And so when I calculate this out, I get something like 0.019 kilogram meters squared for my moment of inertia. Good? Hey, that's all there is to that part. Of course, we'll need this for the second part, so let's go ahead. What I'll do is I'll go ahead and I'll move it up here into the problem for a moment, just so that we remember where it's at. Okay. Well, now, in fact, I'll leave that too. Well, now we're stuck with the second piece, so let's look at this again. The applied torque needed to accelerate it from rest to 1961 in 0.77. Okay, so that's what we're trying to find, the applied torque. Okay. If it is known to slow down from some RPM to rest in 56 seconds. So go ahead, take a second, plan out your solution here. Got it? Okay. Well, there's a couple of things that I think we need to specify before we attack the problem. So first off, we should probably specify what our system is. And here I will choose the disk. And although we're not told specifically what the surroundings are, we can think of at least two things in the surroundings. One is whatever object is doing the applied torque. Okay. So I'll call it, I don't know, object, I guess I'll just call it object 1. We don't really care what this object is, we just know that it's doing this applied torque. And we have object 2, and object 2 we're going to infer based on this. That the wheel slows down when this applied torque is absent. So I'll probably call this the axle. I think what I'll do is I'll call this one the axle, and I'm going to think of this as the frictional force. You know, there's some sort of frictional force that in the absence of the applied torque, the wheel still slows down. Okay? Excuse me. Okay. So let's now plan out our steps. And now that we've got this, let's think about what steps we actually need. And the first one I think of, so steps. The first one I think of is I need to find something dealing with this frictional force. Right? I need to somehow characterize this frictional force, and that will then allow me to find the applied torque. So what I'm going to do is I'm going to find the torque due to the frictional force. And how I'm actually going to do that is looking at the alpha. I'll label this as alpha friction. In other words, what would the angular acceleration be if it were only the frictional force? And then number 2, then we'll find the applied torque. Find tau applied. Sorry. Need to work on the pen. I had to reload everything on my computer, and so the pen got screwed up again. Okay, so let's go at it. Number 1. So right now, I have this as, you know what, now that I think about this, I have this setup is for step 2. Right? This is all for step 2. For step 1, so right now we're thinking step 1. And what we're thinking of is finding things regarding the frictional force. So the system's going to be the same, still just the disk, but the surroundings will just be this frictional force, say axle. And since the axle stays the same for both step 1 and step 2, once I characterize it for step 1, then I can use the same results for step 2. So now we have this. Let's go ahead and think, how can I get, for example, the angular acceleration due to the frictional force? Got it? And my hint to you would be, hey, is this thing constant or non-constant? You'd say constant. This is a constant acceleration. And the minute that you have that, and you notice that I have some information, 1961 RPM, I have an angular speed, and I'm given a time, and I know that the angular acceleration is constant. You say, aha, kinematic equations. Well, what do we have? We have the initial angular speed. We have the final angular speed. We have the time. We have the angular acceleration. We don't have the angular acceleration. That's what we want to find. So we need an expression that includes the angular acceleration and doesn't include the angular distance. And we say, aha, we have that. That is simply the straight out definition of the angular acceleration. Right? And we're good. Now we have this little thing about RPM, but for example, you could say, well, the angular acceleration due to the frictional force, phi, is equal to, well, we have 0, right? That's the final angular speed, this 1961. Now that's in revolutions per minute. The conversion factor would be something like pi, converted into radians. divided by 30, right? Or if you prefer, 2 pi over 60. But there's your conversion, divided by this 56. So the angular acceleration due to the frictional force, what do I have here? I have negative 3.66 radians per second squared. Notice the negative sign, right, to indicate that it's slowing down, right? That's opposite. The angular acceleration is in the opposite direction as the angular velocity. So say, for example, okay, well, here's my disk, and let's say that the motion of the edge of the disk is in this direction. Right. So I can use my right-hand rule. I use my right-hand rule, the shortcut, and if I wrap my fingers in the direction of the motion, my thumb tells me the direction of the angular velocity. So in this case, the angular velocity would be upwards in the positive y direction. This would be the initial. Because this ends up being negative, that tells me that my angular acceleration is actually in the negative y direction. This would be the direction of alpha. Let's go ahead and go one step further here. So I'll call this step 1b. So maybe this is step 1a. I'll go one more step here. So if I call this step A, and I'll call this 1b. Here's the question for you now. Can I characterize the torque associated with the frictional force? You say, yeah, you can. Okay. Now let's go ahead and let's apply Newton's second law for rotational motion. Torque net equals I alpha. Right? The relationship equation between the interaction of the surroundings with the system, right here, and the response of the system, right here. We have now the response of the system. And additionally, we have this from the first bullet point. I was going to call it part A, but not to be confused with 1A. So we have this from the first bullet point, the moment of inertia. We have just calculated how the system responds to the torque. That's in our alpha. So we can find the net torque due to the frictional force. So we'll go ahead and do that. I guess in the most strict sense, these are vectors, of course. So I'll look at the y direction. Looking at the y direction, what I have is the frictional torque equals the moment of inertia times, I'll say, alpha FR. And we're done. Right? You have a value for this, 0.019. You have a value for this, 3.66. And I'll put the negative sign out front. And so you get something, excuse me, I didn't have that one calculated out, shamefully, 0.019 times 3.66. There we are. I get something like the torque due to the frictional force is 0.070 Newton meters. I'm sure. Okay. Well, let's go ahead and we'll store that. So we've got that result. I'll go ahead and store this result too, just in case, you never know. And now we are in a position to tackle the second piece. Of course, you're probably already going at that. And as already highlighted, we have the second system and surroundings right here. We already specified that. So let's go ahead and now apply our relationship equation. Keeping in mind now that we have two objects in our surroundings. Okay. So now we have two objects, and we can still go through and find the angular acceleration, right? We're given enough information for that again. So let's take a look. Let's go ahead, and we'll call this 2a. Let's find the angular acceleration. So let's go through and find the angular acceleration, the net angular acceleration. And again, we're going to use our handy-dandy kinematic equations. We're told a change in omega. We are given a time interval. So we get the net angular acceleration would be, again, equal to negative 1961 times our pi over 30, excuse me. Sorry, bumping the cord there. Divided by, well, now it's this 1.77, right? In the absence of this applied force, it was 56 seconds. Now it's 1.77 seconds. So we get a net acceleration of, I had negative 116.0. Okay. Radians per second squared. Okay. So we should ask ourselves, first of all, well, actually, we should ask ourselves this. We already established, we said, okay, well, if I have a disk and I assume that the edge is moving this way, we've already established that the initial angular velocity is up, and we'll say the torque due to the frictional force is negative. What direction is the applied torque? So the torque due to this applied force. Good. You got it? It's also down, right? See, we still have a negative sign here, and notice that, hey, that angular acceleration is a whole heck of a lot bigger than that due to the torque. That means there must be some other applied force that exerts a torque on this object, and that torque will also be down. So I'll put applied here. Okay. Well, nothing left to do here. We are almost home free. Let's go ahead and polish this sucker off. Well, now we're ready for our relationship equation. Again, we have torque net equals I alpha. I'll look at just the y direction. This is a one-dimensional problem. We have torque net equals I'll put alpha net. Well, we have two torques, and I'll go ahead and put those in. I'll say we have the torque due to the frictional force minus the torque due to the applied force. And that whole thing must equal the moment of inertia times negative alpha. Say net here again. Right, so what I want to say is here I was working very generically. Here's where I actually substitute in the specific torques that are being applied. Well, okay. Let's rearrange. We're after this unknown. So let's go ahead and rearrange. And we have something that says the applied torque is equal to, scoot that over, so I have I times alpha net. Notice I took explicitly into account the directions here. So I'll end up using the magnitude when I substitute this in, minus the frictional force. And again, since I explicitly took into account the sign, I guess for clarity, I'll say, okay, it's the magnitude. And we're done. I mean, we still have to sub in values. If we wanted to do it in terms of variables, this is the mass of the disk times squared, mr squared. Right. I'll call this would be omega naught over what I'll call T, I'll put an S here for short, minus, well, shoot, how did we actually find the torque due to the frictional force? We also multiplied by I. So I have I here, and what do we do? So I have mr squared. We had the initial moment of inertia, and I'll put T and L for long. So if I pulled out all the common terms, for example, if you really wanted to, this is mr squared omega naught multiplied by 1 over Ts minus 1 over T long. So if you don't want to introduce any kind of rounding errors or anything, here is the equation that we would use to actually calculate everything in one go. So let's do that. Let's go ahead now and just calculate out everything. Let's go at it. Equals. Hopefully you can see the advantage to working in variables here. You could have done all of this stuff without the calculator up until this point. 0.687 squared times 1961. Of course, if I just left it with 1961, then my angular acceleration and everything would be in revolutions instead of radians. So I'll multiply by pi over 30 to get it into radians. 1 over Ts, and notice since this one's the short time, this number will be larger than the second term. So I'll end up with a positive value at the end, meaning that I chose the proper direction for the applied torque. Right? In other words, downwards. Remember, I inserted explicitly the negative sign. So the applied torque, when we're all said and done, let's go at it. So I got a value of 4.33 Newton meters. In other words, 1, 2, so 100, something that's about 50 times. I got a torque, an applied torque, that's about 50 times larger than that due to friction. Of course, if I want to remember the directions, what we would say is the applied torque. So if I want the vector expression for this, this would be 4.33. And I'll say this is in the negative y direction. So negative y Newton meters. And there is our final expression. Cool. Okay, well, let me go ahead and pause the video. We'll queue up another one. Hey. Second problem, here we go. A mass m is attached to a hanging mass, little m, by a string passing over a pulley, mass MP, radius r. Determine the angular acceleration of the pulley. Do not assume that the tension in the ropes are the same. Well, gee, this problem sounds a bit familiar. Let's go ahead and draw out let's go ahead and draw out a figure just so that we have an idea about what's going on here. I'm sure that we probably do, but okay, well, we've got hanging mass. We'll call this big M. We call this little m. So, and now it says that we have a pulley. So pulley. There we go. Go ahead and make it a pulley. So here's the problem. Of course, we need a rope. Let's go ahead and get a rope in here. So I have a rope, passes over the pulley down to the hanging mass. Well, we have certainly stepped in it now, haven't we? Let's go ahead. Go ahead and take a minute, see if you can come up with some steps. How are you going to go about solving this problem? Got it? Okay, good. Let's go ahead. We'll assume that this surface is frictionless. Actually, maybe I should have put that in there. Let's go ahead and assume that this surface is frictionless. And of course, we'll say that this is at 90 degrees right now, level surface. You don't have to, it's just going to make life a little bit easier for us. So, off and running. Well, number one, there's at least two things that kind of come to mind first of all, and part of it is due to this, this assertion. So I'll say, well, you know, we should probably find, I'll say the tension in the ropes. So I'll call it Tm and T big M. We should probably find those two tensions. And what keys me into that, even if I don't have this hint, right? If I took this hint out, the thing that keys me into that is I need to know the angular acceleration at the end of the day of this guy. And the question becomes then, what forces cause that pulley to rotate? So if I'm thinking about the pulley as the system for a moment, what forces act on the pulley? You say right away, or hopefully right away, you say, well, there's tension one or little m, there's tension big M. Right? There's those two tension forces. And then there's this support. I'll say the force from the support. Now let's go ahead, we'll assume that that support is attached to the axle. And you could ask yourself, well, what, you know, we'll go through, I guess, and talk about this more. But this doesn't actually play a role, but these two certainly do. Okay, so by way of asking about the angular acceleration, you hopefully saw that you need to find these two tension forces. So if you see that, then that guides you in your steps. Step one, I'll say, let's go ahead and find, say, the tension in the hanging rope. Step two, we'll go ahead and find the tension in the upper rope. And step three is find the angular acceleration. So go ahead, take a shot at that for a moment. And now that you're done pausing and you've taken a shot, hopefully you see you're going to have to actually get all three of these simultaneously. Let's go at it. Okay, well, for step one. Let's go ahead. I'm going to actually do this in terms of forces. And we're taking our system as being the hanging mass, little m. We're taking our surroundings as being the rope, which exerts this tension force, what I'll call T little m, and the earth, which I'll call the gravitational force F of G. We do our free body diagram. Oh, let's go ahead. Let's put a free body diagram in. Say tension force is up, T little m. My gravitational force is down, Fg. And let's go ahead, I'll call that direction positive, y. We have 1D motion. I don't need to worry about the rest of this right now. Let's go ahead, we apply our relationship equation, namely Newton's second law. And since we're in the y direction, I'll drop my vector notation for right now. So I have Tm minus, subbing in my definition for the gravitational force, I have mg equals, be careful here, little m a, the acceleration being downwards. So I'll put a negative sign in, right? I'm explicitly taking into account directions when I move from here to here. So I've got an expression. I've got the tension in that rope is equal to little m times g minus a. So we'll go ahead, let's store that. And this hopefully looks familiar. That is a result that we had previously when we worked this problem. In fact, the approach is exactly the same. So we've had that result, the approach is the same. Let's go ahead for step 2. And here, what I will do is let's take the system to be big M. We'll take the surroundings. Well, what do we have? We have the rope, which is this tension force. We have the earth, which is the gravitational force, Fg. And we have the surface. I'll call surface. And we have that normal force. I'll just call that N. Let's go ahead and do a free body diagram. You know that we're looking at forces right now. We should do a free body diagram. Say, okay, well, our gravitational force is down, Fg. Normal force is up. And in this case, the tension force, as I have it drawn, would be to the right. Oops, yeah, that's right. If I want some axes, I'll go ahead and call y up. I'll call x to the right just to make life easier. Now we apply our relationship equation, and we should look here. We've got forces in 2 directions. We should ask ourselves, which direction do I really care about for this problem? The x direction. Good. You notice the y direction doesn't play a role in this problem. We could, for example, introduce a frictional force. If I made this a friction surface, then all of a sudden we'll have to pay attention to the y direction and the x direction. Okay, so you can see by adding friction, I can make it so that you have a 2D problem. Here, we're just going to look at the x direction. And let's go ahead and apply our relationship equation. F net equals ma. And let's put in the specifics. We have the tension force acting on big M is equal to big M times A. We should ask ourselves for a moment, hey, I've used A here, right? When I was talking about the little mass, should I use A here when I'm talking about the big mass? Survey says yes. Okay. Even so, why can I say that those 2 accelerations are the same? What assumption have I made Haven't explicitly stated it, but what assumption am I making here? We are assuming the string is ideal. By assuming that the string is ideal, we are assuming that it doesn't stretch. That means if one mass drops, the other one has to move at the same rate. So the string is ideal. Should also, we'll say, I guess a second, no, that's it. String is ideal. So that allows us to use the same acceleration in both of those equations. So there's our second one. What we cannot do, so in the past, what we did was that we set, if we go back and look at this problem in a previous video, what we cannot do is set Tm equal to Tm. The tension in the lower rope equal to the tension in the upper rope. That's specifically stated in the problem, and we'll see why that is. And we'll see why can't I set those. If I could set those two equal to each other, I'm done, which is true. The issue is that when you set these two equal to each other, you're making another assumption that will be violated in this problem. Can you come up with it? If you set those two tensions equal to each other, you are assuming an ideal pulley. Ideal pulley. And if you recall, what were some of the ideas about ideal pulleys? So one of them, frictionless. We'll still use that. We'll assume that the pulley does not feel any friction about that axis that I've drawn. But the other one is very important, massless. Is the pulley massless? No, you're told it right here in the problem, right? You're told that it has a mass. So I put the second sentence in because I did not want you to accidentally apply this approximation, that the pulley is ideal. Okay? We are removing that restriction. It is no longer a massless pulley. So we need to figure out how to deal with this. Okay, well, let's go ahead and let's apply step 3. So step 3. And here, let's go ahead, let's write down our system. Pulley. Let's do our surroundings. Good, so we have the ropes. Say Tm, T big M. Yeah, good. We have the earth. Say Fg. And we have the support, right? This pulley is supported. I'll call that a normal force. Now we should ask ourselves, okay, well, I'm going to apply some variant of Newton's second law. You should ask yourself, which variant do I want? Good. We want the rotational version here. Okay, we are going to apply Newton's second law in rotational form. Say, hey, well, how do I know that? Partially, we are asked for the angular acceleration. Angular acceleration of the pulley. That would hint at maybe this would be a good way to go. Now, before we actually start diving into this, we should do our rotational version of a free body diagram. So let's go ahead. Oops, excuse me. Let go at the very last second. Here's my pulley. Let's go ahead and draw in where the forces are applied. So here I have my tension force downwards. I have a second tension force going this way. Oops. Okay. So I'll label that T big M and T little m. I should probably put in the axis, right? I said, hey, you should mention the rotation point. Let's go ahead and use our standard set of axes. There's my axes. And the question is, where's the gravitational force applied on this pulley? Right at the rotation axis. Good. The center, what we would say is the center of mass. Well, I've placed the rotation axis, the axis of the pulley, right at the center of mass. So the gravitational force is right there. How about the support? Where's the normal force from the support located? Also at the axis. I verbally said, hey, let's put this supported at the axis. So here's my, what I'll call my normal force. Okay? Well, let's ask ourselves, I have three directions. Which direction do I really care about for this problem? The z direction. So let's go ahead. We're just going to deal with the z direction. So first off, I'll say, okay, well, I have my torque due to big M, right? The torque due to the tension force due to big M. And I should ask ourselves, what direction is that? I'm choosing the z direction. I need to know, is this torque in the positive or the negative z direction? And remember, how do I actually calculate this using vectors? It would be r cross f. I have a cross product. I'm going to apply the right-hand rule to get the direction. R being the distance from the rotation point to the point of application of the force. So in this case, it's in the y direction. So it'd be R. The force is in the negative x direction. That would be T big M. And so the torque is in positive z. R cross T, I get out of the screen. That's positive z. So I'll leave this as a positive. How about for this other force, the tension due to little m? Good. Negative. R cross F into the screen. That's a negative. So put negative. How about due to gravity? Good. Since this is applied at the rotation axis, the R value that I would use would be 0. So the torque due to gravity is 0. And similarly for the normal force, 0. Good. Last one. What direction for the angular acceleration here? Negative z. Good. Negative z. So I'll put negative alpha. You say, how do you get that, Greg? Well, one way to do it is the shortcut. Let me first point out omega naught, the initial angular speed is 0. And because alpha is defined as, put omega final minus omega initial over some time interval, so this is delta omega over delta t. Okay. Since the initial angular velocity is 0, okay, that means my angular acceleration will be parallel, we'll say angular acceleration will be parallel to omega final. So can I find the direction of omega final? The answer is yes. It's going to be going, if the mass is falling, omega final will be into the page, into the screen, right? I curl my fingers in the direction of the rotation. The angular velocity will be into the page. I shouldn't say direction of rotation. I'll say the direction of the movement. So there we go. I've got it. I've got tau big M minus tau little m is equal to I alpha. Good. Okay, let's go ahead and get rid of some of this. Oh, I can just move that around, eh? There. Get rid of some of that. We're going to go ahead and move this piece up to the top so we have all of our space. And the next thing we're going to do is let's go ahead and use the expressions we have. Should keep in mind, okay, well, this torque, the magnitude would be something like, well, if we wanted to, since we're dealing in magnitudes now, I could say, well, let's do the magnitude of R. I'll label this little m, or excuse me, this one's the big M. R big M. Say the magnitude of T big M. And what's the angle between those two? 90. Right? Don't forget, sometimes the cross product uses the sign of the angle between the two vectors. That's one way of doing it. But in this case, this is 90. So sine of 90 is equal to 1. You can do the same thing. Say, okay, well, I'll do the magnitude of this guy. I guess I should put the vector symbols in here. There we go. Times the magnitude of the force, little m. Same thing, sine of 90. And this will all be equal to negative I alpha. So go ahead. Well, this is just the radius of the pulley, so I get R times big M times A minus R times little m G minus A equals negative I alpha. Here's the next question for you. I've got translational accelerations of the masses, and I've got a rotational acceleration of the pulley. How can I relate those two? And you're making an assumption here. I'm making an assumption. I want you to see if you can figure out what the assumption is. You got it? And I'll say, let's think about the rope on the pulley right here, right? And I want to say something about what that rope is doing. I want to say, does not slip. In other words, as the mass falls, as little m falls, the rope moves over the pulley without slipping. Or a different way to say it is, the pulley rolls without slipping over the rope. We have constrained motion. And with constrained motion, there is a relationship between the translational acceleration of, for example, the rope, and the rotational acceleration of the wheel, namely this. Now, since I'm interested in alpha, I'll go ahead and make this substitution. So what do I have at the end of the day? I have big M R squared alpha minus little m times R G minus A equals the negative moment of inertia of my pulley times alpha. Go. Got it. I'll go ahead, let's move it over here. I have something that says, okay, well, I've got m big R squared. I have a minus, oops, excuse me, I forgot the substitution there, duh. It's the whole purpose. I have minus minus, so I get a plus little m R squared. Moving this term, the moment of inertia, to the other side, I get a plus I. That whole thing, that whole rigmarole is multiplied by alpha. And I get equals to, moving this G term to the other side, I get little m big R times G. Good. We're done. Alpha is equal to, say, mg, put an r in there, divided by, put an r squared, times big M plus little m. Now what the heck? Moment of inertia of the disk. Well, that's just 0.5 mass of the disk, which I call MP times r squared. So there it is, folks. There is the angular acceleration of the pulley. Pretty cool, huh? And in fact, you could go a step further. Say, for example, we could sanity check it. So things like, okay, let's check our units. Well, the numerator has kilogram meter per second squared times a meter, right? That's the numerator. What does the denominator have? Well, the denominator has r squared, so that would be meters squared, times masses, kg. And so we see, okay, well, yes, indeed, the units work out. I get something like 1 over seconds squared. Sometimes I call radians a silent unit. This, you could think of this as being radians here. I call it a silent unit. Sometimes, I mean, it doesn't naturally pop out with any of these variables, but it's in there. So, okay, well, that works. Let's do something else. If we have a massive pulley, what should happen if the pulley is really, really massive? It should be hard to turn, which means the angular acceleration should essentially be 0. We check that. If I make MP really large, right here, we see that I divide by a large number, my angular acceleration is really small. Or if I make the hanging mass 0, my pulley shouldn't move at all. We see if I make my hanging mass 0, pulley shouldn't move. So these all work. So there's that. Why don't we go ahead and extend this just a wee bit further? Now that we have, let's go ahead and just get rid of this whole thing. Now that we have the angular acceleration, we could, for example, go back and find the torques, right? Or excuse me, the tensions in the ropes. We have a relationship between the angular acceleration and the acceleration. We could find the tension in the ropes. Let's go ahead and do that. We'll say the tension for big M is equal to big M times A. Or, if we prefer, big M times the radius times the angular acceleration. Let's go ahead and use this right here. Boom. Say, oh, goody, goody. Now that I have that all out of the way. Say, hey, wait a minute. There's an R, there's an R, there's an R squared. And I can just simply write this as the tension due to the big mass is equal to big M times little m g, all divided by big M plus little m plus this 0.5 mass of the pulley. Let's go ahead and do it for the small one, just for kicks. T little m equals little m g minus a. This is going to be uglier, right? Ugh. Tm equals mg minus, what we'll end up with here? Well, I'll have little m r alpha, but I've got my expression for alpha, so I've got Tm equals mg minus, well, let's see, I'd have m squared g And just similarly, the r's would cancel out, and I would have big M plus little m plus 0.5 MP. Well, that's kind of ugly. Let's go ahead, find a common denominator. Why not? I'd have Tm is equal to, well, common denominator. So this would be little m g times big M plus little m plus 0.5 MP minus m, right? I have an mg here, m squared g. If I pull an mg out, I'd have a minus m left over. Of course, I have this all over this m plus little m plus 0.5 MP. Oh, goody goody. That m cancels that m. And I am left with an expression, the tension in the hanging rope is equal to big M, oh, no, don't do that, little m g times big M plus 0.5 MP. All over big M plus little m plus 0.5 MP. There we go. Pretty cool, huh? Now you might say, why did Greg even do this? Why is Greg even pointing this out? Let me do this. What happens if the pulley is massless? What do these two expressions become if the pulley is massless? The exact same. Do you see that? If I substitute in 0 here, I get big M times little m times g divided by big M plus little m. That's the tension in the rope. And similarly, I get a 0 here, I get a 0 there. I end up with the exact same expression. I told you earlier, I said, hey, if you assume a massless pulley, the tension in the ropes end up being the same. Here, it's not massive, or it is massive, excuse me. So the tensions end up being different. I just wanted to show you that. Okay. So the last thing I'll point out, so that's another good sanity check. These expressions still work. Although it looks ugly, these expressions still work. Okay. The last thing that I'm going to point out to you, and then we'll call it quits after this, is that when we were looking at the pulley, we decided to go with Newton's second law for rotational motion. We used this, and eventually we found an expression for alpha right here. The question I have is, well, could we get more information using Newton's second law in translational form? Okay. Now, thinking about the center of mass of the pulley, did the center of mass of the pulley translate at all? He said, no, it didn't. So you know that this would be 0, right? F net would equal 0. Now, as we showed, once we have alpha, you can go and get expressions for the two tension forces. In fact, we just did that. If I'm thinking about the translational free body diagram of the pulley, what do I have? I have a tension force going this way, Tm. I have a tension force going this way, T little m. I have the gravitational force going this way, Fg. And I had this normal force, N. Armed with an expression for Tm, the two tension forces, and you're given the mass of the pulley, so you can find Fg. If you apply Newton's second law in translational form, you can eventually come up with an expression for the normal force. 2 for the price of 1. You can get the angular acceleration of the pulley, and you can get the normal force on the support. In fact, you can see it from the free body diagram. All right, the normal force, and note I'll use vector notation here. The normal force is simply going to be the tension force in the positive x direction. Remember, I use my standard axes. Then it will be the tension force due to the hanging mass plus the gravitational force acting on the pulley. That's the vector expression for my normal force. You could actually be more specific, right? You could actually substitute in the expressions. Pretty cool. Well, I believe that is enough for today. It's like an hour or something like that. Hey, thanks for your attention. I'll see you next time.